Hello, everyone. I'm Vita, your host for the talk. On behalf of TMLS team, I want to welcome all of you to the MLOps 2020 conference. Feel free to ask your questions during the talk in the chat section, and I will ask your question during Q&A at the end of the talk. This year, we are honored to have great speakers with us. One of them is Yaron. Yaron is an entrepreneur who has deep technological experience in the fields of data, cloud, AI, and networking. As the CTO of Iguazio, Yaron defines the company's vision and a strategy for the company's data science platform and headed the shift towards real-time AI. He also initiated and built Nuclio, a leading open source serverless platform with over 3,000 GitHub stars. Prior to that, Yaron was the Vice President of Datacenter Solutions at Mellanox, where he led technology innovation, software development, and solution integrations. He was also the CTO and Vice President of R&D at Voltaire, a high-performance computing, I/O, and networking company. Yaron is an active contributor to the CNCF working group and was one of the foundation's first member. He presents in major industry events and writes tech content for leading publications like TheNewStack, Hackernoon, DZone, Towards Data Science, and many more. I think we are all excited to hear your talk.
Okay, thank you very much. So with that, I'll start. Before we dive into the solution, let's talk a minute about the problem. So one of the key challenges today, and we also host like a bi-weekly webinar, and we ask the questions, and what are the key challenges in machine learning? So most of the people, they keep repeating that the key challenge is moving from the research environment to production and operationalize machine learning. So to the point where you can actually take a model and the application and the data engineering around it and put it into a business application, and it generates real business value. And why is that so difficult? Because the methodologies that we're using in the research environment are quite different than the methodologies that we're using in production. And I'm going to talk about it and show how we can solve the problem using some open source technologies and some new paradigms of essentially building everything you do directly into production without introducing a lot of hassle in between. Again, the main problem is that when you're running in research, you use notebooks and Jupyter, and you may create very long notebooks that describe all of your working process. You often work with small data sets in order to train. You visualize everything, and you build a model, and sometimes you take this model and put it behind an HTTP endpoint, but that's not real production, because the real production is working with real data that may arrive from ETL processes, from operational databases, data that may arrive from APIs on the internet, from streaming data, from transactions, from updates to locations. And all that data needs to get denormalized and prepared, identifying features and aggregating data into a panel, which will be used for training our model. And sometimes it's a lot of data that we cannot just process in a notebook. The next thing that we need to do once we generated the data set, we need to go and run training. And again, even training may need to happen periodically, every time the data changes, every time the algorithm change, every time we detect some drift in our concepts. And we may want to run the training across more resources because we want to try different permutations, different algorithms to figure out which one is the best. Because accuracy in production is really, really important. You may be happy with 90% in research, but an extra 5% in production could be very meaningful, because someone can sue you because you just generated some gender bias, or because you've made the wrong financial decision. It could cost a lot of money to organizations. So the fact that you need accurate models means that you want to work harder, apply more computation power, and generate better models. So, and finally, once we have those models in production, we have to serve them using real data, real features that were generated from actual customer data, actual location data. And we need to monitor those models in production to try and identify concept drift, to try and identify various problems, performance problems of our model. And if we see some of those challenges, we need to go in and address them. So usually, once a data scientist finishes the research environment, we create a large team that essentially builds the production environment. And that's quite challenging because you may lose some information in the context, and it's very tedious. It's a process that may take a year. Just taking into account, what are those things that we need to do in order to productize anything that we do, whether it's a data engineering code or machine learning model, etc. The first thing after we developed our artifact, whether it's a model or some other software, then we want to translate that into a package that can run in a container, in a cluster like Kubernetes. So we need to build and make those containers. Once we've done that, if we want to address a larger scale, a bigger workload, then we need to think about parallelism aspects. How do we create parallelism to our code, whether it's through data partitioning, load balancing, breaking this to smaller parameter sets and artifacts, distributing the model across various frameworks that know how to handle parallelism. And once we've done that, we go into production. We identify that performance is a key metric. If we serve an application behind the web endpoint, and it takes, let's say, a few hundreds of milliseconds to respond to a customer HTTP request, it may be too slow. Or if we're running training and it takes lots of time, or it doesn't even end if you're using huge amounts of data, we need to find ways to accelerate this process. And there are ways to do it, but it requires engineering. We need to integrate with GPUs. We need to apply parallelism. I need to apply caching to our queries and data access, etc. And as we go further, closer to production, we have to think about how to make it sustainable, how to observe what we're doing, how to make it reproducible and explainable. So we have to apply monitoring and logging and versioning and security. And we also want to automate this workflow so we don't have to go and repeat this ritual every time we change code or data or anything else. So the general idea is that we have to apply CI/CD paradigms and workflows and maybe do canary deployments where we're deploying a new model to production. So all of that effort from companies I worked with can take 12 to 18 months in some organizations. It's also various silos within the organization, data engineering, DevOps, development, data science. And those are some of the things that sometimes hinder the productivity or the operationalization of machine learning. So what do we want to do? We want to try and create a streamlined process which takes concepts from software development and agile methodologies and try and apply them to data science and essentially break the silos between data science and the other groups within the organization. So we want to build sort of a pipeline that knows how to collect data from various sources, whether they're offline sources or real-time sources. We want to apply normalization and data preparation at scale to those data sets. Then we need to train the models based on the generated data set, and then we need to deploy all of that into production. So if we look into what is an example of a pipeline, a machine learning pipeline would usually look something like that. The first step is ingesting data from those variety of sources, because we need to create the feature set used for training. So once we gather the information from all of those different sources, we put it in sort of a pile. Sometimes it may be Parquet files, maybe a data warehouse for base features. The next thing we want to do is build the meaningful features. The meaningful features may require aggregating information over time. For example, how many clicks this user did for the last hour? What is the average temperature in a day, or whatever. Those aggregations are needed because the machine learning algorithms usually would work on top of denormalized data. Sometimes one-hot encoding, sometimes aggregations. joining various data sets in order to build this thing that we train the model upon. So once we created the preparation, we need to run training. Again, we want to run different permutations, different algorithms, different parameter combinations. This is something we may want to do in parallel, so we won't waste a lot of time. And once we've done the training, we want to try our model and run validation logic, essentially testing our model that it is accurate enough. And once we've validated the model, we want to deploy this model as a microservice that listens on requests and responds. Sometimes we also need to combine it with API services, and those API services will essentially get, like, for example, customer ID, fetch all the required features for that customer, contrast it with the model, and respond. So we need this overall pipeline. The way that we're trying to think about simplifying this is that essentially all the data will be stored in what we call a feature store. It's a logical entity. It may actually be implemented across different data stores, but it needs to be registered and indexed in a way that every experiment or every work can just go and access it. And the way that we want to process those different functions, instead of thinking of everything running in a single notebook, we want to create microservices or functions that handle each one of those steps. And by applying this concept of microservices and functions, we can reuse the code. We can have a life cycle for the code. We can develop something, fix it later, have a data engineer apply more optimizations to the same code. So we need those functional elements that will work throughout this pipeline. And on top, we need an orchestration and tracking for the entire process so we can control our machine learning pipeline and our results. So this is the general concept that we're trying to work based on. I don't know if any of you tried to productize a Jupyter notebook, but it's really, really hard. You have to refactor the code. You need to apply operationalization, again, all those processes that I mentioned. So one of the things that we need to think about is already in the stage of development, not necessarily big, huge notebooks that, everything is sort of scrolling, and then the people that need to convert it to something that runs in production will need to really, really suffer or make mistakes, as you can see here in this nice picture. So essentially, we want to already think in production how to instrument our code in the data science phase so we can essentially go and transfer it into production with as little friction as possible. So one of the approaches that we've managed to do it is by introducing a new open source project called MLRun and integrating with other tools like Kubeflow and Serverless engine. I'll describe how it works in general. But the general idea is that you can write your code in your native environment, whether it's through Jupyter notebooks or PyCharm or any other IDE. You need to import some libraries that will be used for auto-tracking your code, because even when you're doing experiments within your notebook, you still want to be able to reproduce your results, to monitor and log all the information of what you've done. And so this is where you want this auto-tracking capability. But at a certain point, you want to run it on a bigger cluster. You want to create it as a microservice that later on could be running in production. But for now, you just want to run something at scale, and you want to be able to essentially just translate your code into a microservice. This is really where technologies like serverless are coming into play. So essentially, I can take my code, I can just add some annotations on my notebook, giving some sort of compiler hints of what I want to do, what kind of resources, data, CPU, GPUs, packages I may want to have running with my code. And then when I'm essentially running or converting my notebook into a real-time microservice, then there is an engine that's going to take this. If it needs to build an image for Docker, it will just build the image. It will run it on a cluster, like a Kubernetes cluster. Sometimes it can actually run it distributed. If we want to run something at very large scale, it could be done automatically, essentially scaling out my workload. And I'm still going to have this tracking capability, regardless if I'm running on my notebook or running as a job in the cluster. So this is the second step, is essentially moving from a notebook into a production capability or a scalable cluster and forming those functions that run in the scalable cluster. At a certain point, we want to start thinking of production. Production requires building a full-blown pipeline. So in order to build a full-blown pipeline, I need to essentially create a workflow, a DAG, or draw some pipeline. And we use a tool called Kubeflow. I'm going to explain about it in a minute, which is essentially knows how to orchestrate a workflow that comprises of multiple individual steps. Those steps will essentially be those functions that we just created. So for example, we have a function for training, a function for data preparation, a function for validation. And if we just change them in a graph and let Kubeflow execute this graph and essentially run all those different steps. We can go and manually go and invoke such a workflow. And this workflow will take our function artifacts from whether it's a code repository or from other means, and run this entire workflow, or can even integrate that as part of a CI process, as I'll show in a few minutes, where we could just create a pull request on Git, and this pull request will automatically trigger the entire machine learning pipeline, which will generate all the artifacts that we need, all the reports that we need, will generate the models, will run testing. Even if we want, it can even deploy the model as part of this workflow. Very similar to CI processes in software development. And at the end of that process, we may want this engine to just throw some notification, whether it's to Slack or to the pull request comment within our Git repository or email or any other mechanism. So with this process, you see what the user is doing. The user is doing very little, and the automation is doing sort of most of the work. You get full tracking of everything, including the experiments, the jobs, all the process of moving your code into microservices is automated, and you could essentially involve different members in that process. So this is an example. There is a question, by the way, is MLrun compared to MLflow? MLrun has the functionality of MLflow. MLflow is mostly monitoring, but MLrun also does orchestration, which MLflow doesn't do. So you can see here that the tracking is essentially very similar to MLflow, but it also does the provisioning, the orchestration of the workflows, the provisioning of creation of the functions, and the fact that it's doing the orchestration means that it's doing auto tracking. Unlike things like MLflow, that you have to essentially instrument your code and add a lot of metadata, because the orchestration engine does the metadata, essentially provisions the resources. It knows automatically what is the metadata for every execution. So it's essentially a lot less work to track solutions using that mechanism. So just talking for a minute about serverless. So why isn't serverless really used in data science too much? Maybe just some model serving functions, because serverless wasn't really designed for backend and data intensive applications. If you look at solutions like Lambda and other cloud functions, you'll see that they're running for a very short amount of time, milliseconds, seconds. They're actually blocked. After a few minutes, they'll actually kill themselves. The way to scale the workload on a serverless function is by applying a load balancer. And they're usually very slow because they're sort of single-threaded, and they don't preserve any state. And in data processing, you want to preserve state. Also, the input for something like a machine learning job may be a data set. I'm giving you a data set, run a model, create a training. I'm not giving you a JSON, which is the typical use case for a function. So the general idea is that you want to apply the technologies of serverless, which means essentially auto-scaling, which means automatic building of your artifacts into something that runs in production, automatic monitoring, logging, all those nice technology, but we may want to apply it using different mechanisms. We want it to run for hours, potentially. We want it to use different mechanisms for scaling, like partitioning and shuffling, and using hyperparameter permutations. We want it to be stateful, and we want the way that we explain the parameters and data sets to be more versatile than just sending you a JSON event. So that's part of the thing that we've done in the different open source projects that we maintain, both in Nuclio and MLRun, is extending this concept of serverless functions to machine learning. And what does it mean, a serverless function? So a serverless function is something that runs as a microservice or a combination of multiple microservices. So I can use parallelism technologies like MPI for Horgood or Dask or Spark or other distributed processing engines as a way to create parallelism for my workload. And then I want to run my workload as part of those microservices. Now, when I'm running the workload, usually for every task, whether it's data engineering or machine learning task, I have inputs and outputs. The inputs usually are things like parameters. You know, what is the type of the algorithm I'm going to use? What are the parameters for the algorithm? Where's the data that I'm trying to read? In many cases, I need also credentials. I'm accessing a remote database. I need the password and the username. I don't want to put them in just plain text. And I want to use data sets. I want to actually pass data sets into my functions and run on top of them. And those data sets can come from various sources, could be databases, could be object store, file mounts, etc. When I'm running this function, when it completes, we want to get a few things. We want to get results, like what's the accuracy of our model. We want to create data sets and artifacts, like models. And we need operational data, like what is the logging? I want to see what's going on with my function. I want to see error notifications. I want to see telemetry, like how much CPU is this function actually consuming. So the general idea is to write your code and embed it into a microservice and wrap it in sort of a sandbox that automatically records all the inputs and outputs. And this is how you can get the capabilities of a tracking system, but without really working so much hard, because this is actually part of the package. The sandbox of tracking your jobs is part of the overall solution and not an afterthought. So I'll answer more questions towards the end of the talk, and we can address them. So another interesting thing is usually when you think about serverless functions, you think about it's going to degrade my performance. So one of the things that we've done with Nuclio, and again, it's very popular, used by a lot of companies, is instead of making it slower, we made it faster. It essentially runs using a parallel real-time engine, which actually runs your code faster. Some blogs I've written in towards data science show a use case of data processing. The same code within your Python will run 20 megabytes per second. If you take the same code exactly, run it inside the Nuclio function, it will run 500 megabytes per second. So 20-something times faster. And why is that? Because of the parallelism built into this engine. So the general idea is that the scaling aspects, the performance optimization, the telemetry, the logging, the monitoring, all those things are part of the engine. They're not something that you need to spend time on that. And that is cutting a huge amount of effort for the developers that work on that code. Other nice things, and that sort of as an outcome, at first it's glueless integration with something like Kubeflow. So essentially you can build those complex pipeline and just stitch function in a pipeline and get it operationalized. And the nice thing is also when you think of functions, which are things that get sort of have a signature, they have a set of parameters and inputs, and they have a set of outputs and results, you can create a reusable function library. So I can create a function that does aggregations, a function that does AutoML, a function that tests models. And each one of those will have a set of parameters. For example, the input data set, the parameters for the validation, and where do we want to dump the report for the validation. So this way you can create a marketplace internal for your team or public like we have in the Git repository that you could just pull in functions and build like a churn prediction application in the matter of a few minutes by just pulling together a bunch of functions. How does it all work with Kubeflow, and what is Kubeflow? Kubeflow is an engine developed originally by Google on top of Kubernetes that provides several functions. One is the sort of something called operators, is a way to automate distributed workloads that are associated with machine learning, like TensorFlow and Spark and others on Kubernetes cluster. It provides a managed notebook framework, and it provides a pipeline automation tool called Kubeflow pipeline, which is what you see here in the diagram. The combination with serverless makes it really easy because each one of those steps in the pipeline is essentially a functions, and every line in that pipeline is essentially passing parameters from one function to another. So this way we can just create a bank of functions and throw those functions into a canvas and make it work, or even launch this notebook or this pipeline, from a notebook. And so there is no real need to work in YAMLs and Dockers and all those things from the DevOps world. A lot of the work that we've done in the integration with Kubeflow is making it very friendly to data scientists. They don't need to write YAMLs or configuration files. They write some Python, and this pipeline will be auto-generated. Okay. And if we're thinking about the bigger picture, this is slightly complicated diagram, but which shows how we can build as an organization an automated workflow based on Git, based on source control for delivering machine learning to production. So let's think about this workflow, because it's essentially divided to three layers: the development layer, the continuous integration, and the continuous deployment. So if we work as a team, as a group, and not with silos where data scientists are one group and data engineers are another group, etc. If we're trying to work as a team between those different groups, we can build this automated workflow and also build the revision control into everything that we do. We don't need to buy expensive products that do our tracking of our processes. We have processes in place. We have Git for source code. We can apply Git for source code and metadata as well. So this is an example of a workflow. Let's assume a data scientist or a data engineer wants to write some code. He can create a new branch. He can open a notebook and develop whatever he wants on that notebook and test it locally. Once he feels it's ready, he can convert it to a serverless function. It's essentially a single command on his notebook, and test it on the cluster just to verify the packages are in place, there are no conflicts, everything is done the right way. And then you could essentially create a pull request telling the other guys, you know what, I've done my work. I want you guys to now go and examine my code. Here you can have all sorts of automated review processes, things that look at the linting of your code and other rules, people that review your code and verify that you haven't done any critical mistake. And once you've done the review of the code, you may want to run an entire pipeline to make sure that this function is working within the entire pipeline the right way, and you merge it into the development release. Potentially, you may also have other regression tests that run, that pull this development release and run some further tests and regressions to verify everything is working. At a certain point, you want to essentially go and productize this release or form a release. Some people work with a single branch. We usually work with two branches, like a development or unstable and a stable. There are different religions here. So you can create a stable branch, tag your version. This is automatically, through automation, can lead to creation of deployment of your models into canaries, meaning only portions of the traffic will go into your model just to verify that it's not really gonna create a critical problem in production. Once you feel it's ready, you essentially promote this model to consume 100% of the traffic, and on an ongoing basis, you want to monitor the service behavior and the concept drift, etc. And if there is a problem over there, you go back to testing and development. So this is an example of a full workflow, which we recommend. Again, for some organizations, it may be too much, because moving to sort of a software practice from data science. So you can create some shortcuts. But again, many of the steps here are fully automated. It's just more of a workflow. The other thing that we need to think is not just the production, not just the training or creating models, is sort of think of the post-production. What happens after we deploy the model? So after we deploy the model, we didn't finish the work. And this is also an emphasize why we cannot really divide between the data scientists and operations people, because even the operational aspect of monitoring the concept drift is essentially running a model. It's running machine learning on the data that is generated in production in order to identify if there is a drift in our concept or a misbehavior of our model. So the way that you can build this with this architecture is that once you've done training and you created a set of serving functions or APIs, those serving functions and APIs, all the ones that are pre-built in the MLrun function bank, know how to generate streams of data with all the requests and the responses. Those requests and responses and other metadata and performance telemetry are pushed into a stream. There could be other functions that listen on that stream, analyze all the information, build aggregations, build analysis, and write it into a time series database, which can be visualized through tools like Grafana. So you can detect drift, you can detect performance hiccups on your model, etc. And on the same time, it can build sort of batch files, large Parquet files every hourly or daily window. And those Parquet files could be later on be compared with reference data, with the real data, the real results, in order to form sort of analysis of the model. And if you identify that there are drifts in your concept or misbehavior on your model, you can apply fixes, which could be either retraining the model on a different parameter set and running ensembles, etc. There is a full demo and an hour session that one of our data scientists did in MLOps Live, and there is a video and tutorial, and everything is also in GitHub, so you can see the code for that full use case. You can essentially just download it and get yourself a concept drift for your model. So this is another example. One example of a customer that is using this approach is Network Appliance. It was public last week that they're using our technology for this and Nuclio and the serverless concept. And just to show you the extreme scale that this could work. So their original architecture was based on building Hadoop, 40-something very large bare metal servers, very expensive, and they need to process 10 trillion data points per month, which is all the telemetry data from all the devices that emit information like CPU latency, problems on the disks, etc. The data is being pushed into the system through files or through streams. Sometimes it supports files, very large support files with all that information. Sometimes it streams using Kafka, sometimes API, REST API calls. So the first thing that you use is functions that crunch the different types of data, essentially go parse the data, and they write it into a time series database. There could be other functions that essentially build aggregations and building like predictive models on top of the time series data to try and detect anomalies on the device's behavior, try and predict other problems. And there are other real-time functions that generate those nice dashboards and alerts. There are also other functions that essentially take the time series data on the database and convert it to Parquet files and throwing it into the data lake. So later on, we can run various analysis, and we also form sort of a backup system. The real advantage is here that those 42 servers, bare metal, are now actually, this entire thing runs on 6 virtual machines in Amazon. Okay, so it's extremely lower cost, and again, it's lower cost than anything else they measured by a factor of 6. Not only that it's lower cost, now you have real-time dashboards based on real-time data. And from what we've seen, and you can see some of it public mentions in the internet, they've saved 90% of the code. 90% less code in DevOps compared to their previous solution. Why is that? Because they only focus on glue logic. All the aspects of logging and monitoring, instrumentation and Dockerization and all that, there's no such code. Everything is automated. So it takes only 10% of the code to build the same solution. If we take another example of a solution, this is a problem of fraud prevention or fraud detection by another one of our customers. So they had a traditional architecture and they want to move from fraud detection to fraud prevention. And fraud prevention requires lower latency. The other thing that they wanted to create more operationalized pipeline where instead of having every 3 months a new software release, they want to have every week a new software release so they can be much more agile. So the traditional architecture for such a solution was essentially having 40 minutes, analyzing the data, doing ETL from a SQL server, doing Hadoop and Spark to aggregate all this information, and then doing batch prediction using our server. It essentially takes about 40 minutes to complete this pipeline. By this time, you can actually empty the bank. And also the release process was very complicated. So this moved to the concept of functions, which could be real-time or batch, essentially streaming all the data transactions from the database through a messaging queue, running real-time analysis coupled with batch analysis using Spark functions, building the models, training on a regular basis, and essentially having the model inferencing listen on an event stream. And basically every time it detects new transactions, it evaluates them, and if it needs to block the customer account, it immediately writes back into the database and blocks the account. So from the first indication of fraud that was generated by the database, because it's essentially monitoring database transactions, until the block was blocked, it takes about 12 seconds. Okay, so it takes its fraction of the time, and now think business-wise, essentially make them prevent fraud. Think instead of chasing money with lawyers and all that, they can essentially block the fraud before it even happened. And the other aspect is they can move to a weekly software release cadence because of all of those functions, they could just be rolled into production on a live system. You could just go and edit something and click deploy and it rolls into production. So that is pretty amazing. So with all that talk, let's move into some real demos. So I'll go into our platform. But again, most of the technologies I've talked about are open source. You could just download. Iguazio just provide a fully managed experience around it. So let's move into a Jupyter notebook. And by the way, I've managed to run exactly the same thing also from Colab or SageMaker or any other managed notebook with very little configuration. Let's first talk about the concept of a function. So we want to write a function, and we want to be able to use this function later on in production or in other places. So the first thing I may want to do is create a function. So let's think about a very simple function. This function opens an archive and writes it into a file system, okay? Just for sake of example. I may want to have various parameters into that function, like where's the target that I want to write to? What is this archive that I need to read from? I want to document that so someone else can do something useful with this function. And here I have a code. Now within my code, I may, for example, want to use logs and logging. I want to write and log some data. I may want to log an artifact, pretty much like in MLflow or another solution. But you see, I'm getting this context object into the function. So this context object allows me to interact directly with a tracking system. Through the context object, I can also grab secrets. I can grab parameters. I can do many interesting operations through that context object, like in traditional serverless technology. So once I have this function, I may want to just export it. So there is a single call called code to function, very intuitive, okay? The nice thing about it is not just converting my code, it's a way for me to also document my code. So I can give it a description, I can categorize it, I can label it, etc. So when it's going into the function marketplace, I can later on just go and search based on label or in other mechanisms, and I could just go and store it. By the way, the function eventually underneath the hood is essentially sort of a YAML file. You can see it later on. It's essentially auto-documenting itself. And then I could just go and export this function into a file. So this file, later on, I could just go and import it and use it in any other location. The next thing I want to do is just import the function. Let's assume I got a URL to a function. There are many types of URLs to the functions. It could be a hub, it's like marketplace functions. There are DBs, like from the function database, local database, etc. Or you could just give it an HTTP or an S3 or whatever URL, it will pick it up automatically. And you see, I can just ask for the documentation. Now, there's no black magic. You see all the documentation of my function based on my doc string in the function. So it's actually also automatically documenting my code without doing any extra work. And then I could just go and run it locally. So when I run it locally, it runs in my notebook, but it wraps it, this run local wraps it in a way that it's also tracking all the information, everything that happened is essentially being tracked locally. You can see the small widget, but there's also a full tracking UI that you can just go and everything that you track will be visible in many different places. This is like MLRun tracking UI. I can just go into every function and I can see the artifacts, the results, the logs, everything. And I could see that by just running this function with the wrapper. It automatically creates all of that. The next thing, I want to run this function on the cluster. I don't want to run it on my notebook. I want to serve a much stronger muscles and resources. The only thing I need to do is just say run. It detects the type of the runtime, which is in this case Kubernetes job. It could be something like Spark or Dask or other distributed engines that MLRun supports. And it's actually creating a pod. It's a Kubernetes microservice. And I'm getting exactly the same experience like running it locally. By the way, I can have this running on my laptop at my home and getting exactly the same experience where the cluster is somewhere in the cloud, because it's using sort of RPC to connect to the cluster and essentially writes back writes the operation and collects back the log and console from the job. So sort of pretty transparently, I can run remotely on a cluster. And sometimes I don't even want to create something on the cluster because I want first some testing to actually load this function in as a Python model, because I don't want to move data around. So you can even do that. You can just convert a function to a Python model and then just invoke it using simple Python commands. So this is this concept of functions. But now let's build something bigger with those functions. Let's build a full-blown machine learning pipeline. So this is all of those things that I'm showing you are all in the MLRun demos report. There are about 6 pretty cool demos. Predictive maintenance, image classification, face recognition, although now it's probably starting to be banned, all this face recognition thing. So let's look at this notebook. So in this notebook, I'm going to do a full-blown machine learning pipeline with AutoML, validation, all the way to production, okay, with a single notebook. So the first thing I'm doing, essentially, I can annotate my notebook, so I can define some packages or other things that will be used by my function, because sometimes I may need special packages, TensorFlow, scikit-learn, etc. We also have a bunch of pre-baked images that people often use, so they don't have to build everything, but in some cases you need extra packages. So you can just go and put some magic commands here in your notebook. The next thing, you just write your function. This is like a data analysis simulator, essentially doing the iris generator, generates the iris data set. And here it's using log data set. It's not using log artifact, it's using log data set, so it's actually structured. It's essentially going to analyze my data and provide some pretty nice widgets around it in the UI. So I'm giving it the data frame, and it's logging that data frame into the artifact repository with versioning and everything. The next thing, I want to create a project, because we want to put all those functions, all this workflow or pipeline under a project. So that's some boilerplating for creating the project. And I'm running this function that I just created that generates the iris data set. So you see it generated the iris data set. It even tells me where this data set resides. You see it's auto tagging information like where's the host that it was running on, who was the admin, who's the owner of the job, all sorts of information is essentially tagged automatically. Okay, and if I'm going to go into the UI, into this specific function, first you see that I may have multiple versions. What I'm seeing here is the latest version, but I may go back in time to other executions, and each execution will have its own artifacts, its own results. Again, I want to look at the artifacts. It's all generated automatically because I used the log data set. I could look at, there was no results here, and I could look at the logs. This is just from this specific run. Okay, and then I want to convert my function into a microservice, so I'm just doing code to function, and essentially now it's a microservice. And I'm just going to register under my project. The next thing I want to do, I want to analyze my data set. But this time I'm really, really lazy. I don't want to write any code, okay? So I'm going to pull in a library function called describe, which is a data analysis, feature analysis function. I don't really remember how to use it, so I'm just going to ask for its documentation. And I see it gets all sorts of information. The most interesting ones are the data set, the data frame, and which column is the Y column, and where do I want to dump the results into. So I'm just going to run this analysis with the input. The input is essentially the output of my generator, and I see a lot of things were generated. Now, this is all because it's running on a shared file system that I'm mounting here. I can actually go and see all those things. Let's just open the plots. And now you see I can see all the clustering of my features. I didn't write a single line of code. Again, I'm too lazy. I just pulled the library function. There are pretty cool library functions there for auto feature selection and other things that our data scientists are developing, and you guys can contribute as well. So you see I have all those feature analyses, feature importance, all those things that were generated automatically just by pulling a function and applying it to my data set. The next thing I want to do is build an entire pipeline that comprises of data preparation, analysis, classification, validation, building models. So again, because I'm too lazy here, I'm just going to pull in pre-baked functions for AutoML and verification. But the nice thing is that you can share. Someone could write a function and store it in a database, and then someone else can pull it and work on it. A third guy can go and improve the performance of the function and create a new tag. So that's it. So essentially, I'm going and creating a Kubeflow pipeline DSL. Kubeflow allows me to describe every function. Every function has inputs and outputs. So the first step is building my containers. The second step will grab my container image and build an ingestion function. The third step will analyze the ingested data. Essentially, it will take the ingested data output and use it as an input for the analysis. In the training, I'm using AutoML, and I want to specify the algorithms that may be used for my training, and maybe what is the criteria for selection across those algorithms, and so on. And then I have validation function and model deployment function. So I can combine real-time functions like model serving and batch functions in a single pipeline. And the only thing I need to do is just save it and run this pipeline. And essentially it's going to run. I'm going to show you to that in a minute. And when it finishes, it generates an output with all the metrics of what I've done. So essentially, this is running in Kubeflow pipelines, which is also provided as a managed service on our platform, but you can have the fun of installing it yourself. So in Kubeflow pipeline, you can track all the different pipeline runs and go to individual run, and then I could see each one of the steps. You can see the first step, generated data, the second step, conducted training, and I see a bunch of plots that were generated from this library function. I can see the analysis of my data sets, okay? It did the deployment, so it essentially deployed the model to a microservice, real-time microservice. It's also doing a test on a different test set, so I can compare the behavior. And finally, I'm running testing on my production function. So I take the test set, and I'm running it against the production function, and I want to measure the latency of my model. So I don't have to find out in production that, yeah, it's accurate, but it's, perform really lousy. And all those things were generated automatically for me. And again, you could just go and view all those things. For example, let's look at the training function. The training function is an AutoML function, so it essentially has multiple iterations. It was running multiple iterations, and it chose one iteration as the best result, and it shows it as sort of the leading result for the overall thing. And if I want to see each one of the artifacts, I can see that. Also, I can look at the actual function that was used with the code. I can go into the functions and, for example, look into the code of that specific version to verify that that's really what I wanted to run. I can look into artifacts in that project. Let's take this test set. Because I used log data set, it not only logs a preview of my data, it also generates the statistics of my data set. Now, the nice thing about it, I hardly wrote any code. Okay, as any of you, I wasn't cheating, you see. All of that was generated automatically. So there are a lot of tracking systems, but the problem with those tracking systems, you have to put a lot of metadata and data into those. Here, for example, looking at the artifact, I can see how was it produced. It was produced by a run, and this is the URL of the run and the name. And those were the sources of the data sources used in order to generate that output. So lineage, all of that is done automatically without any human involvement. And you could also put labels on your data. Beyond that, one thing that we mentioned that we can integrate that with Git. So there is a project that we demonstrate how you can actually do all that thing as part of the Git workflow. So you can essentially build automation using GitHub Action to listen on the pull request. And once there is a pull request, it will automatically, you can just go and say /run in your pull request, and it will automatically run the workflow, respond back into your pull request with all the results. So that gives you tracking, that gives you explainability. You ran this version of the code, this was the result in accuracy, those were the data sets and everything. It can even fire a Slack message, which is pretty cool. And you see all the other things that I mentioned. And any one of you can just go and clone this repo and run, and it works. Okay. And now we also talked about having real-time functions. It's not just batch functions. So if you go into Nuclio, which is again an open source project, I can actually go and see different versions of the functions. If I really want to look into the code, I'm going to look into the code. It was auto-generated, you see, from Jupyter. I can still go edit the code. And this is a very simple code for model serving. You see, it has a load and predict. And that's it. And I can configure aspects in that function, resources, CPUs, GPUs. I can configure the triggering mechanism that I want it to be on a stream or an HTTP. It's as easy as saying, you know what, let's put it on a Kafka stream. Here's the topic, and now it's going to be on a Kafka stream. Okay, and if I want to build canaries, then you just go into the API gateway and edit that, and I could just shift traffic from one version to another just by pulling the lever up or down, and that's it. So okay, so with that, that's my my demo, and I see there are a lot of questions, so let me try and address them if we have more time.
Hi, all. Thank you, Yaron, for your great talk. It was really interesting, and you're right. We have a lot of questions. I try to ask them all. One of our attendees asked, what will be the constraint of using something like Airflow for ML workflows compared to Kubeflow? And I asked another question that might be a little bit related. What is the difference between Kubeflow and Airflow?
Okay, so Airflow is really more used in for Hadoop area. It's more sort of oriented towards data engineering workflows, and Kubeflow was designed as sort of a native Kubernetes thing. Kubeflow is based on a mechanism called Argo, which is also open source project with a lot of contributors. It essentially what it knows how to do very well is integrate with Kubernetes and with container architecture. So essentially every step in Kubeflow is also a container, which makes life easier in terms of how you package your code and all of that. And you can see that also integrate with sort of the tracking system. So the concepts of artifacts, and all that integrated into the solution, the concept of experiments and what is good experiment and bad experiment, the ability to have other resources, like I want to mount a Kubernetes volume into a step or apply secrets and all those things. It's very hard to do in Airflow. We do see that Airflow has potentially more integrations around Hadoop tools, etc. But Kubeflow has a marketplace for components that also stitch to all those things as well. But if you're running on Kubernetes, Kubeflow is a way more native approach. Again, it attaches to like Kubernetes volumes and secrets, and you can configure your Kubernetes object as part of the workflow, etc.
Thank you. And
also much more modern in terms of the architecture, which is obviously where people want to go.
Great, thank you. Another related question is that does Kubeflow related to Firebase?
No, Firebase is really sort of a Google project for mobile and database, etc. Kubeflow is an orchestration tool, and it's entirely open source.
Great, thank you. And another question is that in the real-time fraud prevention example, you went from 40 minutes to 12 seconds. What was the major contributor to the increase in speed?
So the first is moving from a batch architecture to a continuous architecture. So instead of every 40 minutes or so running an ETL job and then analyzing the data in a batch, what we do is essentially stream the transaction directly from change notifications of the database. Every time there is a transaction on the database, it fires an event which gets analyzed. And that's also a different architecture on the data analysis, because you need to think about windowing strategies and real-time aggregations, real-time feature vectors. It's all running using streaming technologies. So it's a different architecture, but the essence is, instead of doing batch, is essentially processing the events as they occur.
Okay, great. And another question is that keeping track of the artifacts, is Emeron also using the Kubeflow's artifacts, or is it Emeron specific?
So it is, Emeron is managing the artifacts. The advantage of something like Emeron that it runs everywhere. It doesn't require a Kubernetes cluster. And many data scientists just want to work off their laptop initially without a cluster. And then just attach it to a cluster and get a bigger And also, Emerun is a lot more automated than Kubeflow. So just even this widget that you see in Kubeflow, if you would not use Emerun to create this widget, you have to generate JSON and place them in some directories and all of that. Emerun is automatically, when it registers the artifacts, it also registers them in the Kubeflow mechanisms, so it will be automatically visible in the system. Again, it's more automated in those areas. See, and I haven't done a lot of work to log my artifacts. Because I use this context object, the artifact automatically fell into the right place with the right jobs, and everything got connected automatically. That's not the case with Kubeflow. You would need to do a lot of manual boilerplating.
Great. And another related question, somehow similar, are there significant differences with Kubernetes operator in Airflow and Kubeflow?
So again, Airflow wasn't designed as a Kubernetes resource to begin with. It's using Celery, and everyone familiar with that. And over time was sort of adopted to Kubernetes. Airflow is also very relatively old compared to Kubeflow and Argo. And those were designed as a first-class Kubernetes citizen. So the native integration of Kubeflow and Argo on top of Kubernetes is much better. And also, it's a much more modern architecture based on microservices.
Thank you.
And it's more associated, again, with machine learning. All the concept around it is around machine learning, but it can also run aspects of CI. As you've seen, I can actually run CI. I did the build of the image, and I did the data engineering and machine learning all in a single workflow.
Okay, and if you have time, we have another question.
Sure.
May I ask? Okay. Can Emerun extend to deep learning use cases like image classification?
Yeah, it's actually a great question, because if you see what I have here is essentially a deep learning pipeline example, which is downloading images, doing image classification, image labeling, running training using MPI. This is another example in the Emerun example repository, which is doing distributed training using distributed Horvath, essentially running the training on top of a directory of a lot of images and creating an image serving model. The other thing that Nuclio, which is used for serving, is very powerful. It supports many different variations of serving, not just the basic, getting a vector of numeric data and responding. So in this example, you can actually see that you can send to Nuclio the actual JPEG image of a cat, and it will tell you if it's a dog or a cat.
Yeah.
Just, so again, it's a very powerful set of tools, not just for playground.
Thank you. Thank you so much, Yaron. That was all the questions. And if you want to add something, now you can do that. And again, I want to really thank you for the great talk.
Okay, sure. Thank you very much, everyone. And we encourage you, again, most of those solutions are open source projects. If you don't want the hassle of installing open source, come to us. We'll give you a sort of a cluster pre-integrated to work with. And it works on-prem and in the cloud. It's not limited to one.
Thank you. Thank you so much. And I want to invite you all to, if you want to connect with other attendees, you can do that via the networking button on the left side. And I strongly encourage you to visit the Expo booth. You can find our sponsors there. Thank you so much.